Okay, so day 5 of Unit 3, we're going to be talking about another way to determine limits. And sometimes when we're finding a limit, we're just plugging in the value that x is approaching, and we get an indeterminate form. Okay, so there are a few different types of indeterminate forms. Infinity times infinity. Indeterminate forms are values that cannot be determined. That's why they're called indeterminate. Okay, just to list a few. Indeterminate forms. And the two indeterminate forms that we're going to be concerning ourselves with the most are infinity over infinity and 0 over 0. Okay, so L'Hopital's rule is a rule that lets us recalculate a limit if we initially get an indeterminate form. So, given two functions f of x and g of x, if the limit as x approaches a of those two functions is both equal to 0, and they're written in some ratio, then this limit would be 0 over 0. And if I get that indeterminate form, I can recalculate the limit by taking the derivative of the top and dividing by the derivative of the bottom. That's what L'Hopital's rule is saying. The limit of the function is equal to the limit of the top over the limit of the bottom. This does not mean to use the quotient rule to calculate the limit of the function. It literally means to take the derivative of what's on top and divide it by the derivative of what's on bottom, and then recalculate the limit by plugging in a. Okay, so for the first example, find the limit if it exists. So the limit as x approaches 1 of the natural log of x over x minus 1. Well, when we initially plug in 1, we get 0 over 0, which is one of those indeterminate forms I said that we can use with L'Hopital's rule. So L'Hopital's rule says I take the derivative of the top, divide by the derivative of the bottom, and then recalculate the limit. So, recalculate the limit, the derivative of the top over the derivative of the bottom. Simple as that, right? Now when we recalculate the limit, I get 1 over 1, which is 1. So sometimes, when using L'Hopital's rule, it doesn't work the first time. So, in calculating this limit, when we plug in infinity, e to the x goes off into infinity, and x squared goes off into infinity. So we do get an indeterminate form, infinity over infinity. So we're going to use L'Hopital's rule and recalculate the limit. Now, I like to do a little h over top of an equal sign, and that tells me that I've used L'Hopital's rule to go from the line above to the line below. So I know what I'm doing when I rewrite the derivative of e to the x, which is e to the x, and the derivative of x squared, which is 2x. Well, what happened was we used L'Hopital's rule, and if we plug now in infinity, I still get infinity over infinity. So we're going to have to do L'Hopital's rule again. And now I get infinity over 2. which is infinity. Therefore, the limit does not exist. Remember, we said if the limit is infinity, positive or negative, then the limit is said to not exist. It does not exist as a good answer. In fact, it's the answer I prefer. Okay, so for the next example, find the limit if it exists. So, as x goes to infinity, the natural log of x blows up, goes to infinity, and the cube root of x also goes to infinity. So I have another indeterminate form, infinity over infinity. So L'Hopital's rule. And indicating that I'm using L'Hopital's rule, and we recalculate the limit of the derivative of the top over the derivative of the bottom. And the derivative of the bottom here is 1/3 x to the negative 2/3, which simplifies to 3 over x to the 1/3, which equals forgot to rewrite my limit, which equals zero. All right. So find the limit if it exists of tan x minus x over x cubed as x goes to 0. Well, right off the bat we can see that the tangent of 0 is 0, 0 minus 0 is 0, and x 0 cubed is 0, so we get 0 over 0. We have another indeterminate form. We're going to use L'Hopital's rule. We will recalculate the limit at the derivative of the top over the derivative of the bottom. However, still, when I plug in 0 for x, I get 0 over 0. So we're going to L'Hopital again. Before I do that, I'm going to rewrite secant squared x minus 1 is tan squared x. So the derivative of tan squared x is 2 tan x secant x, we'll have over 6x. Sorry, 2 tan x secant squared x, because the derivative of the outside would be 2 tan x, and the derivative of the inside would be secant squared x. My apologies. However, this is still 0 over 0. Even when we cross the 2 and the 6 out, make it a 3. So we're going to do L'Hopital's rule one more time. derivative of the top is a product rule. Now when I go to plug in 0, I get 0 plus 1 over 3 . So this limit is 1/3. Okay, so remember, when using L'Hopital's rule, there's only two indeterminate forms that L'Hopital's rule applies to. And that's infinity over infinity and 0 over 0. When I look at this limit, I get 0 times negative infinity. Definitely an indeterminate form, but not one that I can use L'Hopital's rule for. So I'm going to make this look like a problem I can use L'Hopital's rule for. Now when I plug in 0, I get infinity over infinity. Technically, I get negative infinity over positive infinity. But nonetheless, an indeterminate form that L'Hopital's rule does apply to. Derivative of the top over the derivative of the bottom. Which simplifies to negative x, whose limit is 0. Okay, find the limit if it exists. Well, the secant of pi over 2 is, I think, 0. The tangent of pi over 2 is infinity. So what's 0 minus infinity? Well, it's indeterminate. So it's an indeterminate form. But it's not one that I can use L'Hopital's rule for. So we need to make this look like something I can use L'Hopital's rule for. Well, secant is 1 over cosine, and tangent sine over cosine. So I could rewrite this as the limit as x approaches pi over 2 from the negative side of 1 minus sine over cosine. And now when I plug in pi over 2, I get 1 minus 1, which is 0, over 0, which is an indeterminate form that I can use L'Hopital's rule for. So my answer is 0. And who would have thought that if you took an infinite number away from 0, you would end up with 0? Okay, so for the final example, something a little tricky. The limit as x approaches 0 from the positive side of x raised to the power of x. Well, initially when you plug in 0, you get 0 to the power of 0, which isn't 1, and it's not 0. It's indeterminate. So I have an indeterminate form, but not one that I can use L'Hopital's rule with. So I have to do a little bit of manipulation to make it look like something that I can use L'Hopital's rule for. So what we'll do is we'll let x raised to the power of x equal or be some function, and we'll call that function y. So y is a function of x. And now if I take the limit, or excuse me, now if I take the natural log of both sides, remember, this x can be pulled down in front, and I have this. Now if we were to apply this limit to both sides, this we've already solved. That was a few examples ago. And it was equal to 0. So the limit of the natural log of y as x approaches 0 is equal to 0. But I want to know what the limit of y is. So if the limit of the natural log of y as x approaches 0 equals 0, then the limit as x approaches 0 of y must equal e to the 0, which is 1. So my solution is 1. The limit as x approaches 0 from the positive side of x raised to the power of x is 1.